So my name is Yonit. I'm from Israel. I'm a data scientist at Windward. I came to Windward 3 years ago from a PhD in the Weizmann Institute, where I actually did research on the human genome. So I switched from the human genome to ships. Quite similar, right? And today we're going to talk about modeling ships, machine learning and deep learning models, and the role of the data scientist in creating a machine learn-based product. So why ships? Well, before I came to Windward, I never been on a big ship. In fact, I never even saw a very large ship. How many of you ever seen a very, very large ship, something in the size of a building lying on the water? Well, quite a lot, more than I expected. But still, it seems like we live on land and ships are at sea and we have nothing in common. But you probably all own something from wood or paper. Well, most of the wood arrives to Germany from Sweden via shipping. And cars, well, they travel worldwide via shipping. And in fact, 90% of the world trade is via shipping. So most of the things that you consume in your country arrive there via shipping. So our lives are full of ships without us even being aware of it. And you know what else? Ships have accidents. In fact, 1 out of 10 ships will have an accident in the next year. And an accident at sea is something huge. It has environmental effect, financial effect, and of course, many, many people lose their lives at sea. So this is just an example of one accident that occurred this year. It occurred in the Kerch, which is a place in the Black Sea. 2 tankers carrying gas exploded, millions of dollars lost, huge ecological damage. It took them days to put out the fire, and 11 people dead and more missing. And this is just one example of an accident. There are many such every year. And the question is, can we as data scientists predict such accidents? So let's pause for a minute from talking about ships and talk about cars because it's more intuitive for us. So we all know this fellow. Well, he's a risky driver, right? He drives fast. He might use his gun while driving. Well, hopefully we are all safe drivers. We obey to the traffic law. We don't use our cell phone while driving, hopefully. So it's quite intuitive to understand that different drivers have different probability of having an accident. So why not apply the same logic on ships? The only problem is that most of us don't operate ships, so we have less intuition on this world. But what if we could model the unique operational profile of every ship in the world? Maybe then we can actually predict accidents. So what's the data here? Ships transmit their location. They do it for safety issues. And satellites receive these messages, and we at Windward buy these messages, more than 100 million transmissions every day. And after a huge algorithmic work that took us a few years, we got to this, the Windward system, which is enable us to see the full historical path and real-time location of every ship around the globe. So can we go from these 100 million transmissions a day to models that predict accidents? So it's all about context. The location of the ship is not enough to tell us anything about the probability of an accident. We need to know what a ship is doing and why. Let's start with what a ship is doing. So these are 3 pictures of paths of ships. And I can only tell you that the red line indicates low speed. But for me, they look quite the same. But if you ask a captain, he will immediately tell you that these are completely 3 different activities. So the left one is anchoring, which is throwing the anchor, and it can happen at the middle of the sea. The middle one is mooring, which is anchoring in a safe place, such a port or a dock. And the right one is drifting, which is turning off the engine and letting the winds and the current take you along. And it can indicate a problem with the engine or fishing. So these are completely 3 different activities. So we tagged and analyzed thousands of such events and let machine learning model to train and detect these activities. So in our production system, we now detect these activities in real time and historically. And these are not the only things that ships can do. Ships can only meet with one another. They can turn off the transmissions. They can change course. And we have machine learning models that detect all these activities in real time. So we know what a ship is doing, but in order to have the full context, we also need to know why. And the why can be because of geography, navigational, weather, and many more. So let's start with geography. So just like on land, there are specific areas of interest at sea. So at Windward, we have the polygons of all the countries and the ports and the docks in the world. So we can actually quantify how much time a ship spent in all the ports or in a specific ports. But we can actually do more complex things with geography. For example, we can actually quantify how much time did the ship spend sailing at dangerous depths at night. What does it mean? Let's dive into it. So we have the water depth all around the world, and we can also cross it with a draft of the ship. So when we look at a ship, we only see part of it, the part that is above the water. But there is also a large part that is within the water. This is called the draft of the ship, and it differs from one ship to another, the dimensions. But if we know the draft and we know the water depth, we can actually quantify how much depth is left beneath the ship. And if it's too shallow, then the ship is in danger of touching the ground. And this is a grounding accident, which is very severe. We can also cross it with day and night information because, of course, at night everything becomes more dangerous. And eventually we can actually quantify how much time did the ship spend sailing at dangerous depth at night. And this is a very good risk predictor. Let's talk about navigation. So just like on land, there are also maps, navigational maps at sea. For example, in purple, it's a separation zone, and there are two traffic lanes. So let's watch this movie. Try to follow the red circle on the top. It's a ship moving. It's a bit hard with this lightning, but it's quite hard to understand what's happening here. It seems like now there is a dangerous event, but we don't know whose fault it is. Now let's add context. Again, the red circle in top, this is a separation zone, and the ship is now crossing a separation zone and sailing in the opposite direction, almost having an accident. So this is a very risky behavior, and we can only understand it if we add the context, the navigational map. Another thing that we can do with the navigation is anomaly detection. So drifting is when a ship turns off the engine and let the wind and the current takes it along. And it can happen because a ship is waiting to enter a port, or because it is fishing, or it actually has a problem in the engine, or it's doing something illegal. So how do we know when what is what? So we applied clustering algorithm to detect drifting areas, and we train them every month because they can change seasonally. So, for example, here's a big cluster is a waiting area before Rio de Janeiro. And now we can actually detect other ships that are drifting outside of drifting clusters. So we can actually say that they are doing something or illegal, or there is a problem in the engine. And this is, again, a very good risk predictor. So now let's talk about weather. Well, it's quite intuitive to understand that weather affects shipping, right? But it's not only about which weather you encounter, it's also about the behavior in bad weather. Because some ships encounter bad weather all the time. It's just part of their route. The question is, how do they behave when there is bad weather? Let's see an example. So this is, again, a picture from the Windward system. And we see a path of one ship. But we can't say much, so let's add the context. And the context here is the wave height map. And we see that the red circle is actually the eye of the storm. So this ship is sailing directly towards the eye of the storm. Very weird behavior, right? Let's look at another ship that was in the same area at the same time. And we see that it actually taking a round turn to avoid the storm. This is much better behavior. And in fact, it's a very sad story. This ship was called the El Faro. It sailed directly towards the eye of the storm. It sank and 30 people lost their lives. And it was found out that they had delayed weather information. But from this sad story, we now learn how important it is to model the behavior of ships in bad weather. So we now have a few hundred features describing the full operational profile of every ship in the world. And if you want to model this problem, what's left to have is labels. But unfortunately for us, there is no such place as the ground truth accident database. So we created one. We gathered accidents from the news, from open sources, from sources that we bought, and we analyzed and tagged each one of them and created an accidents database. So now that we have features and labels, we can actually apply machine learning models. And we decided to use XGBoost, which is a tree-based models, and we separated to 4 different accident types, 4 different models. Why? Because different accidents can have different risk predictor. In this picture, you can see on the left, it's a grounding accident. On the right, it's a collision. They are very different in the risk predictors and also in the outcome. So now we have these great XGBoost models, and we asked ourselves, can we utilize deep learning to solve this problem? So now we need to go all the way back from the features to the raw data. And our raw data is a time series data. So for each ship, we have the full path of the ship, which is a timestamp with the X and Y coordinates around the globe. So how do we use this time series data in a deep learning network? So we can actually compare this data to sentence completion, which is more intuitive to us. So if I want to create a network that will complete this sentence, when I am cooking, I am careful not to get burned from the. So if I go a bit backwards, I see the word burned, and I can add these 3 options, sun, oven, and fire, with the same probability. But if I'll have the full context of the sentence, if I go all the way backwards, I will see the word cooking and understand that I need to add the word oven here. So our time series data is very similar. It's not enough to know the end of the end of the path, just where the ship is located now. We need to have all the full path of the ship to know where it was, also in the beginning, to get the full context. And that we take these messages, this time series data, and we interpolate it to have the similar gaps between the messages so that every ship has its location every rounded hour. And we enrich this data from the vicinity of the ship. For example, the weather or the depth or the day at night at the same time and at the same location that the ship was. So we need to find a network that will enable us to add this context to our data. And we chose TCN, Temporal Convolutional Networks. I won't go into the architecture of this network because of time limitation, but feel free to ask me about it later on. And we chose them because they were shown to be very good with time series in the literature. So we decided to start with the relatively easy problems. The easy problem is detecting or predicting the ship class. The ships have different classes: tanker, cargo, service, and a few other. And it's relatively easy for us because we know the class of every ship in the world at Windward. And the class correlates with the behavior. So we decided to start from solving this problem, and we created this TCN network and trained it for a few hundred epochs, and really got to a model with very good accuracy in predicting the ship class. And now we applied transfer learning to solve the accident prediction problem. Why? Because we thought that the TCN network that was trained to detect the vessel class, the ship class, already captured the perception of what is a ship. It probably already got to the speed and the depth and the day and night and all the things that we try to capture in our feature engineering. So this network already captured the ships, and now we just changed the label and retrained it a bit to solve the accident prediction problem. And it worked quite good, and in fact, we got to very good models. But actually, the XGBoost models and the TCN model performed quite similarly. And the question is, what is better? So I will leave this question open for now. And I will also tell you that, remember the Kerch accident that I told you about that happened in the Black Sea? Well, our models performed very good and actually predicted this accident before it happened. Or more precisely, our models gave the ships that had the Kerch accident the highest score for accident prediction already before it happened. So we have these very good XGBoost and TCN models. And then the next question is, who is the user? Who can benefit from these accident prediction models? And the user here is insurance companies. Why? Because they want to better price the risk, and because they have loss prevention teams. These teams are dedicated to prevent the next accident from happening. They detect risky owners and put them on a special program to let them know what to change in the behavior of their risky ships. And we can help them do that. We can help them detect the risky owners with the risky ships and also tell them what to change. So this is a place called Lloyd's of London. It's in London, of course. And this is where marine insurance started. It's quite traditional. Most of the people who work there, well, their father worked there, their grandfather worked there, even their grand-grandfather worked there. It's so traditional that they even have a quill and ink where they write the total losses in a special book. Real quill and ink. So this is Windward, and this is Lloyd's of London. Suits, T-shirts, suits, plank every noon. You see the difference, right? So the next question, or the next challenge that we faced was, how do we take these models that predict accidents and come as a startup from Israel to these clever people who have been doing their job successfully in the last few hundred years and tell them, hey, use our machine learning models, trust us. And in fact, this is a question that is asked in many industries now. How do we gain trust, or how do we make traditional industries use machine learning, AI, deep learning? But also, this is usually the step where we say, hey, product, sales team, we are the data scientists, we created these amazing models, now you go sell them. But today I want to tell you that in fact, we have data science tools to help assist bridging this gap. How? Well, we become impactful in the user's eyes, and we gain trust in Windward, in the data, and in the machine learning model. Let's start with becoming impactful in their eyes. How do we do it in data science tools? So we model one ship at a time. We look at ships and we give the probability of an accident to ships. Why? Because we as data scientists want to model what's closest to the data. But in fact, insurance companies are interested in the risk of a group of ships called fleet. And they need to know the risk of the whole group, because they just need to choose if to insure or not to insure the whole group. So how do we give a risk to a group of objects that we just modeled? Hey, this is a data science question. So we thought about two options. We can average the risk of the ships, or we can actually model this problem. Why? Because a group of ships might have the same owner or the same manager or operator, so they might have the same budget for maintenance and the same criteria for hiring crew, and the risk of one might influence the risk of another ship. Another thing that helped us to become impactful in their eyes is probability versus loss. So again, our machine learning models produces probability. For example, 0.02 probability of collision. But in fact, insurance companies are interested in loss, or more precisely, expected loss. How much do they expect to lose in the next year on a ship? So there is a missing component in between the two objects, and this missing component is a severity. Severity is assuming that there was an accident, how much would it cost? And this is a very hard regression problem. So we are now working on solving and modeling this problem, and also creating weights for different accidents in different populations. So now let's talk about trust. How do we gain trust in machine learning models? So this is a picture from a meeting that we have with which later on became our first insurance client. And in this picture, you can see Ali and Rotem. They are my colleagues from the business unit in Windward. But you can also see Ido and me. And we are data scientists. And we flew there to explain their CEO and underwriters and actuaries all about our data, our machine learning techniques, our models. And in fact, we found out that we are the best speakers for our models, the data scientists who build them. And since then, every potential insurance client gets to have a workshop with one of the data science team, with their actuarial team, to really gain trust in the data and understand the techniques and even test it for their scenarios. So trust is not only about people, it's also about the data. And we found out that we can't just give the prediction or the output of the model as is. We also need to give the user the ability to interpret the results by himself. So when we give the user the model score, we also give him the full operational profile of every ship to really gain trust in the data and understand what the ship have been doing in the last year. And last but not least is explainability. So this is a very important topic these days with machine learning model, how we unravel what's the explainability behind the models. And a recent algorithm or paper came out describing SHAP. SHAP is a very cool algorithm that takes inspiration from the theory of games. And what it actually do is it gives us a SHAP value, which is a marginal contribution of each feature to the final score of the model. Let's look at an example. So this is the output of SHAP of one model for one ship. So the score of the ship is 0.02 in the model. And the base value to the left is actually the average score in the population. And the question is, which features contributed to pushing the score upwards from the base score, from the average of the population? So each bar here indicates one feature, and the size of the bar indicates the size of the contribution. The red bars indicate features that contributed to uplifting the score, and the blue bar indicate features that brought the score downwards. And in fact, this is a real score for one of the ships that had the accident in the Kerch, and these are its features. But we can actually do more cool stuff with these SHAP values. So we have 4 accidents prediction models, and we want to combine them all to an overall score. So we apply a linear transformation on the score to get an overall score. But we can actually apply the same transformation on the SHAP values, and they can be additive. We can even make it more complex. Remember the severity weights that I talked about? We apply them to the scores, and we can apply them also to the SHAP value. So eventually, we have the full explanation of the model, which features contributed to the final overall score of the ship. And just before I finish, I will tell you that actually we decided to go with the XGBoost models because of all these explainability issues and because we really need to be clear and to unravel the mystery behind the black box of the machine learning models. And these days, it's more easy to do it with XGBoost models than with deep learning models. So we can predict accidents, and we can even help prevent them. We learn from the experts their model, no shortcuts. We marry data science and AI capabilities with maritime expertise to gain insights on the maritime domain. Data science tools can help build trust in models and bridge the gap to machine learning, to bring machine learning to traditional industries. It's true for the marine insurance industry, and it's also true for many other industries that are now introduced with machine learning and deep learning. And data scientists can be out front. That's it. Thank you very much for listening.